Okay, so today we will be continuing some of the material from Lecture 2 of our IAP course on causality. We are finishing up in this some material on identification in the non-parametric setting. And then Lecture 3 is going to take us through some material on identification in parametric settings. And that will all become more clear as we go on. So where were we? One of the things that we started setting out to prove in the last lecture, in Lecture 2, Part 1, was that factorization in directed graphs implies a form of Markovianity in those directed graphs. This is an extension of what, or a DAG version, I guess, of what we proved for undirected graphs. So, kind of on the way to proving that, I said, okay, we're going to have to go through moral graphs and talk about undirected graphs. We've done some of that already. And so far, what we have is we know that if some probability distribution, P of x, factorizes according to some undirected graph, G, and then we have a separation statement in that undirected graph. So in this graph, say that the set A is separated from the set B given S. Then these together are going to tell us something about the probability distribution, conditional independences in that distribution. In particular, A is conditionally independent of B given S. And another thing that we proved is that if we have a distribution that factorizes according to a DAG model, then that distribution is also going to factorize with respect to now the moral graph, which we were denoting G bar. So we'll make all of these G bars. Now what we want to do is add something over here that says if A is independent, is deseparated in the graph, the DAG G, given from B given S, then we would like the factorization at the DAG level, and at the DAG level, this deseparation statement to imply a corresponding conditional independent statement in the probability distribution. And essentially what we're going to want to do here is show a version of deseparation implying a separation in a corresponding moral graph. However, we're going to have to consider not this full distribution at once. Just as a quick example, think of x1, x2, both going to x3. Then the moral graph is x1, x2, x3, all completely connected. So here, there are no separation statements, and as we'll see with our definition of separation in DAGs, which we will call deseparation, we have x1 is independent, is deseparated of x2 unconditional. So the way that we're going to kind of go about recovering this is to consider subsets of our nodes, and then take the moral graph on those subsets. So we'll come back and kind of fill in this proof diagram as we go through the lecture today. Okay, so to start, we need to say what we mean by this symbol when we're talking about separation in directed graphs. So we're going to build up to that definition and talk over a few kind of key concepts that you'll find throughout, reasoning about DAG models. The first is the notion of a collider. So if we have a path gamma in a DAG, so let's take gamma 1 up to gamma m. Just a series of nodes such that each node is adjacent, so there's an edge either from gamma m to gamma m plus 1 or from gamma m plus 1 to gamma m. So we can go kind of up and down in this graph along this path. This path is going to have two types of nodes, so we will call a node gamma m in this path, a collider if the arrowheads on the nodes before and after gamma m in this path kind of collide or meet head to head at gamma m. So that's if you have gamma m minus 1, gamma m plus 1, both with arrows into gamma. And then otherwise, we call gamma m non-collider. Okay, so given those two types of nodes in a path, we're going to define a notion of whether or not a path is blocked, and that will be split again into these two cases. So given a DAG, this is kind of our setup, DAG G path gamma in that DAG, and a set that we're considering S, subset of the nodes. We call node in that path one of three things. So first, we will call it a blocked non-collider if, well, of course, it needs to be a non-collider, and then additionally, we'll say that it's blocked if the node is in our set S. Next, we will call a collider blocked this is almost just the reverse, that we don't want gamma m in S, but actually we don't want gamma m or any of its descendants in S. So we can write that concisely by saying this closure of the descendants. So this is both the descendants of gamma m along with gamma m itself. If that intersection with our set S is the empty set. Then otherwise, we're going to call a node unblocked. Okay. So we're going to put this together. I'm just going to check the recording here. Looks good. We're going to put this together into a pathwise notion instead of right now. We've just been thinking at the level of nodes. And we'll call path gamma and a DAG G. We'll call that path deconnecting. Given the set S, if all nodes in the path are unblocked. So all it takes is one node to be blocked, and then this path will no longer be deconnecting. The idea is that you're going from node to node to node, and if you ever encounter a node that's blocked, you have to stop, and you can no longer use this path to establish this kind of deconnection. And if xi and xj are the endpoints of this path, so if gamma is a path from xi to xj, we call xi and xj deconnected. Given S. Okay. And finally, our notion of deseparation is just going to be that there are no deconnecting paths. So we'll just write that here, and then I'll give an example and try to make all of this a bit more clear. So we say xi and xj are separated given S if there does not exist any deconnecting path. And this is what we are denoting, this is what we mean when we use the notation xi deseparated from xj given S. And what we can do is we just extend this to sets in the natural way. So if instead of nodes we're talking about sets, A and B, so we'll have A is deseparated from B given S. If when we take all xi's in A and all xj's in B, then those are pairwise deseparated given S. And I won't write that out here. And then finally, as we did in the case of undirected models, we can kind of put all of these together into a set. So this set I of G is going to be all of the deseparations in G. Great. So let's get some practice with this. So we'll use our DAG from lecture 1 when we were talking about some genetic modification experiment on mice. And we'll think about a few of the possible paths in here and whether or not they're deconnecting. So to start off with, if we had our path being x1 to x2 to x4, and we had our conditioning set be the empty set, then this path is going to be deconnecting because the only node on that path is besides the endpoint, of course, the only other node is a non-collider, and if we check our criteria for whether or not a non-collider is blocked or unblocked, we'll see that, okay, as long as the non-collider is not in the set, then it's going to be unblocked. So kind of the default status for non-colliders is that they're unblocked. They only become blocked kind of if you put them in S, if you're thinking about kind of S, the empty set being the default, and then kind of building the setup from there. That's usually how I'm thinking about it. Now, if we were to instead take S to be x1, then this path is no longer deconnecting. And what this is supposed to represent, if we go back to our idea of what the experiment was, is that we have a genetic modification that might affect Mickey by, say, shifting his weight the average weight of that distribution that we're sampling the mouse Mickey from by 2. And then that in turn is going to have an effect on cheddar, on the weight of cheddar. Now, if we block this path, there can still be an effect of the genetic modification along this other path, but if we already know what x2 is, and we've kind of accounted for x1's effect on x4 through this path. And in particular, if we were to condition on both x2 and x3, then we would have x1 and x4, or x2 and x3 being x1 and x4 being deseparated if we condition on x2 and x3. Okay, so next, let's consider this path down here, x2 and x4, and x3 with both of the edges from x2 and x3 into x4. So if we were to start with, say, this set x1, this is not a deconnecting path. So what this is kind of representing is that if we know, if we have x2 and x3, and we know whether or not there was a genetic modification, there's actually no more deconnecting paths between x2 and x3. The only other possible one is down here. And the only way that the weight of Mickey and Minnie are going to be kind of associated to each other is through whether or not that there's a genetic modification on both of them. Now, what happens is that if I add x4 to this conditioning set, now we see that this is a deconnecting path because this is a collider and x4 itself is in the set S. What this represents is, say that, okay, we've already kind of explained away any sort of connection between x2 and x3 in terms of the genetic modification. But now say I also show you Cheddar's weight. And Cheddar, say, weighs a lot. Maybe he weighs 30 grams or something. And now I look at the weight of Mickey and say he actually has a very low weight, say 20 grams or something. Well, then it's much more likely that Minnie has a high weight to kind of account for the high weight that we're seeing with Cheddar. So if we kind of know something about the child of these two variables, that is going to kind of induce some connection between them. And that holds equally true if, instead of conditioning on x4, we were to condition on x5. This is just now knowing, say, that their grandchild Gouda has a high weight is going to induce some dependence between our beliefs about the weights of Mickey and Minnie. Okay, so we've defined the notion of separation in DAGs that we're seeking to use, and now let's define some connections between deseparation in DAGs and separation in moral graphs. And in order to do that, as I alluded to with the example where we had x1, x2 going to x3, and we kind of take a subset of the nodes before doing the moralization operation, we're going to explain what kind of subsets that we want to be looking at. So in particular, we're going to be looking at subsets of nodes which include all of their ancestors, which are going to be subsets that we call ancestral. So we say subset of nodes V and X is ancestral. And our DAG G, if when we take the set of ancestors of V, inclusive, so we'll also take the nodes of V themselves, this is actually equal to just V. So basically, we're not missing, we don't add anything by taking all of the ancestors. Another thing that you could call this would be upwards closed, or ancestrally closed. Okay. And then just to formalize kind of the operation of taking this subgraph and just looking at the nodes x1 and x2, we'll introduce the term induced subgraph, and we'll also get some notation in this definition. So if we have a subset of nodes V and X and a DAG G, the induced subgraph this is denoted G with brackets and then the V inside, is the DAG with nodes V and the edge xi to xj if and only if xi goes to xj in original graph G, and of course xi and xj are both in our set V. Okay. And small claim is going to be that if P of X factorizes according to a DAG G, then Px V, just the marginal distribution over B, factorizes according to the induced subgraph. And we also need that B is ancestral. Okay. The idea here is that if we go back, I guess you could see this in two ways. First, if we go back to the structural causal model, we just have this ordered list of kind of causal mechanisms. What we're doing is, if we're thinking about P of X as coming from a structural causal model, is just going up to all of the nodes in this ancestral set V and getting rid of the equations for the rest of the nodes. And then it is pretty clear that it's going to factorize according to the induced subgraph. Alternatively, if you want to just view it in terms of the probability distributions themselves, so all you're assuming is that this factorizes according to a DAG G, you don't care if it came from a structural causal model or not. What you would do is basically, when you're marginalizing out, notice that all of the terms for things that are not in this ancestral set, all of those just marginalize out, so we can kind of write out that distribution and factor it into the parts that we have in this factorization according to G of V, and then a bunch of things that integrate away to 1. And if you don't believe it, just check that. Okay, so now that we've started thinking about ancestral sets, we can relate deseparation in DAGs to separation in their moral growths. So the theorem we want to prove is that if we have disjoint subsets A, B, and S, such that A is separated, deseparated in B, but from B given S in our DAG G, then they are going to be separated in the undirected graph, the moral graph of this induced subgraph G of V, where V is the ancestral closure of A, B, and S. Okay. Just as a note, you can actually show the converse of this, which was one of the problems in the first homework. We don't need that for the sake of what we're doing here today, but this kind of completely characterizes the notion of deseparation. Great. So how will we go about proving this? So we're going to start off, this is basically a proof of the contrapositive. We're going to start off with a deconnecting path. So if we say, suppose gamma is a deconnecting path, or sorry, is a connecting path, in bar GV, given S, and let's say this is for sets A and B, B. And what we want to show is that if this separation statement doesn't hold, then this separation statement won't hold. So we're going to change this kind of connecting path into a deconnecting path in the graph G. Okay, so let's consider the edges in this path. Well, one kind of annoying thing is that this path, all of those edges don't already exist in G, because we might have added some edges when we were doing the moralization. So those edges that we can, that are in G, so if xi and xj being an edge in this path are, so if these are adjacent in the graph G, then the path is unblocked. This kind of segment of this path is unblocked. At xi and xj. Because otherwise, if the path gamma was blocked at one of these nodes when we go to G, that means one of these has to be in the set S. Okay. The other case is that if we have an edge where that is not true, so the edge is not actually in G, we're going to have some child of x and j, which is kind of the one responsible for introducing that edge when we're doing the moralization. And this could be easy to just kind of replace our edge xi to xj with this structure if xk is unblocked. So we'll say if the descendants inclusive of xk intersect somewhere with S, we use in our new path, so let's call this new path gamma prime. We'll say it's gamma, but with xi, xk, xj, kind of replacing that original edge between xi and xj. We can kind of think of, okay, we are repeatedly doing this to apply to get these new paths gamma prime to go from the original connecting path in the moral graph to a deconnecting path. So if this holds, that's super easy. If not, so if this intersection is the empty set, well then, how did xk kind of get into our set V? We're saying it's not an ancestor of anything in S, so we have to have that xk is in either the ancestors of A or B. So let it be like, say, A, and either A or B is a descendant of xk. Then we let gamma prime be gamma, but we replace all of the edges kind of after xi. We replace them with the path that we just take directly from xk to this variable a. And this path is going to have to be unblocked because we already said none of the descendants of xk were in S. So these are all descendants of xk. The path can't be blocked at any of these points. And what I mean, all the edges after xi, this really depends on whether or not we choose a, this little a, to be a node in A or a node in B. So if it's a node in A, and we kind of start on this side, so we have A going into xi, and then this path keeps going this way and hits B. If we choose something in A, what we would want to do is kind of think about it this way. So we will replace, I guess, from xj, we'll go now down to xk, and then to the descendant in A. Otherwise, if the node that we picked was in B, we would kind of keep going this way, and then when we get to xi, we're going to replace the path. So I think this will be more clear with an illustration. If we have an original DAG model, being this complicated guy, so here are our two nodes, A1 and A2, and then we're coming over here and connecting up with our node B. And this is some graph G, and notice that in this case we have B being equal to the set A1, A2, B, and S. And then this is just exactly the only nodes in this graph are ancestors of at least one of these nodes. So this is already, we can kind of think about this as after we've done this kind of ancestral lization or whatever. So there could have been other nodes below S or something, or below B or A that we're not including. So looking at just this, the moral graph is going to be a graph with the same nodes being adjacent, and additionally we're filling in whenever we have two nodes which are the parent of a common node. So we have these two additional edges introduced. And the idea is that if we were to have a deconnecting path between this at a just connecting path in this graph, say we're considering this path between A1 and B, well then, by our construction, we can transform this into a path in the DAG. And what we're going to do is, well, we already said we can take any of the edges that were common in both of the paths. I guess let's go step by step. So we first take this edge that's common in both of the paths, then we look at the edge here. What we have to do is replace that by this collider. So this is kind of the first case where it's easy to just replace the edge with this collider path. And then when we get to this edge, we have this harder case where, okay, actually none of the descendants of xk are in our set S. So instead of replacing it and just kind of following the path along back to up to A1, we're using the fact that xk has a descendant A2. So what we've done is we've transported the path gamma into a different path, gamma prime. Great. So that proves our relationship between the notions of separation that we have. And this is actually going to let us completely flesh out this proof. So what we do is we will add throughout this kind of marginalization, or kind of taking the induced subgraph idea. So we'll have to make all of the things on this kind of right-hand side the marginal version. So we had that P of x factorizes according to the DAG G is going to imply the marginal distribution. Pxv factorizes according to the induced subgraph G of B. Okay, and then now we're just going to follow through. So we started with G of V. That implies that Pxv, the marginal distribution, factorizes according to the moral graph G of V. This separation statement we want to hold in G of V and the bar G of V, the moral graph. And what we've just proved is that the deseparation statement in G of V is implying the separation statement in its moral graph. So this is just for V equals the ancestor set of A, B, and X. So that's kind of the additional thing that's allowing us to say that Px of V factorizes according to the DAG of the induced subgraph. Great. So this actually wraps the proof up. We have that if the distribution factorizes according to this graph and it's deseparated, so if it's deseparated right in the induced subgraph, then it's going to be deseparated in the original graph. And these together give us this conditional independent statement. Okay, so now we can use our connection between factorization and conditional independency DAG models, along with kind of these tools of the expanded interventional graph that we developed in lecture 1 in order to say some things relating interventional distributions and observational distributions. So first, we can call this kind of an action observation exchange. We're going to say that if I is an intervention, on A, so going along with our notation, that was just saying the intervention targets are equal to A. Okay. And then suppose that in our expanded, so our interventional causal graph is G of I. This is just the one where we introduce this kind of zeta I variable and have it point to all of the nodes in A. So in this graph, if that zeta I variable is independent, there is deseparated from Y given sets S and A, then so this is a deseparation statement, and we can conclude a conditional independence from it in the distribution that factorizes, which is in our case Pxi. So the conditional independence that we can conclude, if we write that out, is going to look something like this, and I'll just already simplify it for the sake of writing the theorem out, is that if we have y given s equals s, and then importantly this is a do intervention on A, then this is actually equal to the conditional distribution, just given A equals A. So that's the exchanging the action, the observation. The important part, right, is that we'll see that it's important that this is going to be a do intervention. So in the proof, right, just our factorization implies conditional independence is telling us that Pxi, so in this distribution, with the one extra variable zeta I, that if we have y given s equals s and a equals a, then it doesn't matter, whether or not that zeta I variable takes on the value 0 or 1. And then this was kind of a consistency property of this notation, was that this probability distribution is exactly just equal to the distribution just over x of y given s equals s and a equals a. So this is just the kind of that intervention indicator is indexing into the observational distribution. And then this distribution is equal to essentially the interventional one, which we could either denote by the I superscript up here, or we have this special notation in the case of do interventions where we kind of say which distribution that we're looking at by writing this do A equals A, right? And then the last step to show that these two are equal is we just need to get rid of this conditioning on A equals A, and that's perfectly fine to do in the case of do interventions because that's a probability one event. So we're essentially just dividing by 1 always. We're multiplying. This always happens. So conditioning on it isn't really telling us anything about the distribution over y. Great. So as you can see, once we have the machinery of deseparation implying conditional independence, and when we're thinking about everything in terms of these interventional causal graphs, which are augmented by the intervention indicators, this theorem is pretty easy to prove. Another theorem that's going to relate the interventional and observational distributions instead of having us replace the intervention with observation, we'll just be able to kind of drop it all together. So in this theorem, what we're going to have is that if V, some set of nodes V, is deseparated in this graph GI from zeta I, given some set S, then we can just completely drop our action here. So if we had this probability that we're trying to look at in the interventional case, the conditional probability is just equal to this probability. And this is, again, super clear from just relating these two distributions in the conditional distributions in the probability distribution P of I. Okay, great. So we'll combine the conditions of these two theorems to give us a way to identify causal effects. That's kind of going to generalize the identification idea that we looked at in the first part of lecture 2. Okay, so what we're going to see is that if we have a set that pretty much satisfies those two conditions, so if we have S which satisfies those two conditions, we'll call those the backdoor criterion. And we could call S a backdoor adjustment set for Y and A. So this is for always this thing that we're trying to estimate. That's if first the intervention indicator is independent of Y, given, or is deseparated from Y, given S and A, and we just have this marginal independence between zeta I and S, this marginal subset. Okay, and these two parts, the reason that we call this the backdoor criterion is that this part captures the notion that S is blocking all what we would call backdoor paths. So we can kind of divide the paths between A and Y into paths that are kind of causal, so they're actually just directed from A to Y, or paths that start with edges both out of A and Y. So, you know, some nodes up here, as well as maybe some paths down below. So the backdoor paths are going to be the ones that have edges both into A and Y. And what this is saying is that if we add in this zeta I variable, and we're conditioning on S and A, right? So if we condition on A, that's going to block kind of all of the paths with edges out of A. So the only possible ways that zeta I and Y could be connected would be if we take zeta I back up away from A, and then this is saying that, okay, actually S is sufficient to block the rest of those paths. Right? And then this part is saying that S does not contain any descendants of A. Right, so zeta I can kind of only access the other variables through A. If we're not conditioning on A, now we no longer have to worry about going up here. The only things zeta I could be connected to are things that are descendants of A. And that's because, you know, we're not conditioning and opening up any more colliders and forming any more deconnecting paths. Great. So that's kind of the interpretation of what this backdoor criterion says. And now, pretty simple, we can use these conditions that it satisfies to show that we can use the adjustment formula to identify our interventional distribution for Y. Right, so this is Theorem 6 in our notes, which just says if S satisfies the backdoor criterion, then the distribution the interventional distribution is equal to some overall values of S, or integration, if this is continuous, of this is exactly what we alluded to in the last lecture when we would call a variable, set of variables, a adjustment set that satisfies this formula. And the proof here is really just something that looks like what we proved in the case where we said we only had one variable S confounding A and Y. So basically what we do, it's just going to be a sketch maybe, is we use the law of total probability. So that is going to write this interventional distribution basically as something like this. And then we're going to use the first part of the backdoor criterion to change this into conditioning. And then we're going to use the second part to just drop the action on A altogether. So before we wrap up, let's discuss some motivation for why we spend all this time developing conditions to check, in this case, whether something is an adjustment set. And what we want to do is show, where this can go wrong. So what if we used the adjustment formula for a set that actually is not an adjustment set, or we don't have a proof that it's an adjustment set? Well, then we can obtain biased estimates of the thing that we're trying to estimate, just inconsistent estimates. So the example that I want to give is called the low birth weight paradox. The idea here is that we're just looking at some observational data about whether or not smoking will be our action or intervention here. We're looking at some data between smoking and risk of developing lung cancer, say. Then actually, sorry, the low birth weight paradox is not with cancer. This is with infant mortality. This would be maternal smoking. So whether a mother is smoking some while they're pregnant, and then this is infant mortality. If you just look at the correlation between these two, in most studies, what you'll find is that higher rates of maternal smoking are correlated with higher infant mortality rates. And the paradox here, or the supposed paradox, is that if you then stratify your data, so you look just at some variable S, which is, say, whether or not the infant has a low birth weight. Well, what's been observed is that the infants with low birth weight, actually maternal smoking is associated with lower infant mortality, so better health outcomes for the infants. And if you're a doctor looking at some observational data like this, you're like, really? Like, is this saying that if I note that somebody looks like their kid is going to have a low birth weight, say 6 months in, I should be like, oh yeah, I recommend smoking. That's really going to help, increase their life expectancy. So that's a causal question of whether or not you should be recommending maternal smoking. And the kind of solution to this paradox is, well, actually, you shouldn't, because what we're doing here is probably something like this, that maternal smoking probably has an effect on birth weight. These would actually be, that association would be observed in the data. And then there's probably some unobserved variable, say U, that is something like malnutrition of the mother. Okay, so we don't observe this. And malnutrition, you would expect, could lead to higher rates of infant mortality and lower birth rates. So if there's a causal effect here that we're trying to kind of disentangle, and if we conditioned on this S variable, what we're doing is we're opening a deconnecting path, A to S to U to Y. So S is not something that we should use in the adjustment formula. So something that you don't kind of need all of the causal machinery to notice here, all the kind of graphical machinery, I guess, is that this is a case of stratifying or measuring these post-treatment variables, which a trained econometrician or something would tell you that's not something that we want to do. Let's just always exclude from our kind of adjustment set anything that is post-treatment and just use pre-treatment variables. But that can still, in some cases, go wrong, where you have something like a pre-treatment variable up here that isn't downstream of either the treatment or the outcome. But if you have some additional confounding between that variable and either of these variables, then even conditioning on that here is going to open up a deconnecting path. So now we have kind of the tools to rigorously show what constitutes a valid backdoor adjustment set. That's not going to be the only type of adjustment set. So maybe I'll start beginning my kind of closing remarks. There are kind of these more complete conditions for both adjustment and for identification in general. So kind of the one for identification is the one that I want to call out here, which is called the do calculus. This is a set of sound and complete rules for manipulating interventional distributions and turning them into expressions that just involve observational distributions. And there's an algorithm that just repeatedly applies these rules of the do calculus called the ID algorithm. Right, so the idea behind this is you put in your graph and what you want to identify, and the ID algorithm will return one of two answers. It will either say, okay, here is a formula that identifies that thing, or it will say, here's a certificate witnessing the fact that that cannot be identified. Basically, an example of two graphs where they have the same observational distribution, but different interventional distributions for the one that you're asking about. Okay, and just of note, that thing that it will output is often referred to as an identification formula. Okay. Another interesting thing to think about is the fact that we have only considered identification formulas where that kind of right-hand side involves just strictly observational data. So you can also ask questions about what happens when you have data from some interventions, maybe not the interventions that you want. Right, so we might have something like A to M to Y, and know, maybe there's like some confounding between some of the variables, and you might not have interventions on A, but you have interventions on kind of a proxy or a surrogate for it, like M. And then you can ask, okay, well, can I still identify the causal effect? And then the identification formula can include not just kind of these observational quantities, but interventional quantities from whichever interventions you say that you have.